So, welcome to this lecture on classical crypto systems. Today we shall be essentially talking about some important definitions which exist in very old literature of ciphers, and we will be seeing that many of the concepts essentially as we proceed in the course are also applicable to the modern ciphers that we have in the present day. So, today's objectives will be essentially to talk about some of the important definitions behind cipher designs, and then we will be talking about a very important principle which is known as Kerckhoffs Principle, and then discuss about some important class of old ciphers which are called as monoalphabetic ciphers. An example of that is a shift cipher, and then about polyalphabetic ciphers which are called Vigenere ciphers, and then discuss about affine ciphers and use our previous days concepts of Euler-Torsion function to find out the size of the key in affine ciphers, and then conclude our discussion with a note on permutation cipher. So, to start with, essentially today we will be discussing about crypto systems. So, as we have made a fair amount of idea that when we are discussing about crypto systems, then crypto systems are essentially used to encrypt the given plain text. So, we have been provided with a plain text and we are supposed to kind of transform these text and modify them and produce a text which is different from the plain text, and this modified plain text is something which is known as the cipher text. Now, the objective is that the cipher text should not leak any information about the original content of the plain text to a person or a third person who does not have a possession of a secret material which is known as the key. So, the key is essentially used to configure a crypto system. That means that it essentially defines the mapping of a plain text to the given to a particular cipher text. So, there are essentially two very broad categories of ciphers. One of them is called symmetric key crypto systems, where essentially the encryptor and the decryptor, that is the sender and the receiver, use the same piece of key. Okay, the key is the same. That means that if you need to kind of communicate using a symmetric key crypto system, then it is imperative that both the sender and the receiver essentially shares the keying material beforehand. So, essentially there should be some other channel, some other secure channel through which the sender and the receiver have shared this piece of information. So, and opposed to, so that adds to the cost of the symmetric key crypto system. That is, there is an inherent assumption that initially there is a secure channel through which the encryptor and the decryptor have shared this piece of information. Now, a very innovative the other type of ciphers which essentially relies upon mathematical assumptions is something which is called a public key crypto system. Now, in a public key crypto system, there are two concepts of keys. So, as we saw that in a symmetric key crypto system, the sender and the receiver have got the same piece of key and they need to kind of exchange the key beforehand. This problem is some sort of alleviated in context of public key crypto systems, because there are two concepts of keys. One of them is called the public key and the other one is the private key. Now, when we are using for encryption, then the public key is used for encrypting. That means this piece of key which is known to everybody can be used for the encryption. So, ideally anybody can encrypt, but when you are decrypting, then you need some key which is known as the private key, and essentially which is not known to everybody apart from the only person who is supposed to decrypt the information. So, that means that in a public key crypto system anybody can encrypt, but only a particular intended person can decrypt the information. So, that means that if Alice would like to communicate with Bob, then what Alice does is that Alice uses a piece of key which is known as so if Alice wants to send a piece of information to Bob, then Alice uses the public key of Bob, because Alice uses the public key of Bob, and when Bob receives this information, then Bob decrypts it using its own secret key or private key. So, that means that it sums out like this, that is, pictographically, if Alice and Bob are two persons who are communicating between each other, and Alice has a public key, say call it I will define this as we proceed more in the class, but this is just to have a flavor of the topics that we will be discussing. So, there is a public key called PK, and Bob also has a secret key, call it SK. Okay. So, when Alice wants to send a piece of message to Bob, then what Alice does is that Alice encrypts this M using the public key of Bob. Okay, so the PK is Bob's public key. So PK is Bob's public key. Okay, and SK is Bob's secret key. So what Alice does is that Alice encrypts M using PK and sends it to Bob. Now when Bob needs to decrypt this, then Bob decrypts this using the decryption function, call it D, but the internal key is essentially SK. Okay, so that means Bob uses its own secret key to decrypt this information, and this should be back to M. Okay, so that means that completes the decryption procedure. Now there are some interesting points here, like about the key. So it should be that PK is known to everybody, and PK also should, doing the encryption also should be easy. But when you are kind of decrypting, then you need this piece of information called SK, okay, which is the secret key. And another important, mathematical, the base on which public key crypto systems rely upon is that from PK, which is a public information, extracting the SK, that is the secret information, should be a computationally difficult task. So this should not be easy, okay, and this gives us we do not really have exact definitions in computer science, which actually proves that there are some problems which are actually hard, okay, but we also but on the other hand, we have got some common number theoretic problems which have actually for many times actually, it has been they have been evaluated and they have been found to be difficult. So they are kind of assumed to be difficult, but we really do not have any rigorous mathematical proof to justify that they are indeed difficult problems. Okay, so there are essentially some gray areas, some place where we kind of need to assume, and based upon these assumptions, which are actually withstood for a lot of analysis, lot of attack methods, okay, we actually develop the science of public key crypto systems. Okay, so we will see more concrete examples as we proceed in the class. So then we come to the definitions. Okay, so again back to the definitions, that is, so we had the symmetric key crypto systems and public key crypto systems, which are essentially two broad categories of ciphers. Then I would like to kind of comment upon a very important principle which is there, is that the basic assumption is that the entire system is completely known to the attacker. So if you build a cipher, then you have to publish that cipher so that everybody knows that cipher. But what is not known to the attacker is only the secret piece of information, which is called the key. So this principle is known as the Kerckhoffs Principle, which says that the crypto algorithms are never secret. Okay, so the idea is that our experience shows that secret algorithms are weak when exposed. That is, if you kind of have an indoor algorithm and you rely upon an indoor algorithm which has not been scrutinized properly, then experience shows that secret algorithms are indeed weak. Okay, and there are several examples of such type. Okay, if you do not properly criticize your algorithms, properly analyze your algorithms, then there are a lot of possibilities that they may be weak inherently. Okay, so therefore the idea is that make a new cipher and publish it, and so that people analyzes them, and then only you can be kind of sure that your algorithm is, or rather you can be more confident that your algorithm is secured. Okay, and secret algorithms, and it has been found that secret algorithms are never remain secret, that finally somehow they leak. Okay, so it is better to find the weaknesses beforehand. So therefore the idea is that whenever you make a cipher, assume that the ciphering algorithm is known to the attacker, but the attacker does not know the piece of information which is secret, which is called the key. Even then it should be difficult for him or her to obtain the plain text from the cipher text, and also it should be difficult from the attacker's point of view to obtain the piece of information which is known as the key from the cipher text. And there are some more evolved models of attacks which says that it should be also difficult to obtain the key even if you know the cipher text and the plain text. Okay, so the idea is that you have to do more and more kind of stricter analysis of your crypto algorithms to gain more confidence that your algorithm is indeed secured. So this is the broad picture of how you are communicating. You have a plain text, there is an encryption algorithm, there is a key, you generate the cipher text, then you receive this piece of information, you decrypt that using the key and you obtain back the plain text. Okay, so these algorithms, that is encryption algorithms and decryption algorithms, can be either symmetric key. If they are symmetric key, then this key and this key are the same, that is the encryption key and the decryption key are the same. But if there is a public key crypto system, then this is essentially the public key, but this piece of information is the private key. Okay, so there can be other uses of this public key private key, which in context to signatures, where essentially we use the private key to do the encryption operation, because we are signing using the private key, but we verify using the public key. So anybody can verify, but only the person who is supposed to sign can sign. Okay, so that is another application of, very important application of public key crypto systems. So in little bit more formally, your crypto system is essentially a 5 tuple, where there are 5 tuples. The members are the plain text denoted by P, which is a finite set of possible plain texts. Then you have got the C, which is a finite set of possible cipher texts. So this could be alphabets, this could be numbers, this could be bit strings, okay, but they are essentially derived from a finite set of possible values. Then K is the key space, which is a finite set of possible keys. And then the idea is that for all K which belongs to this, for all key which belongs to this key set, there should exist an encryption algorithm. I mean, there should exist an encryption rule, and there should exist a decryption rule, such that for each, if you have got a P and C, that is P to C mapping, there should be a corresponding C to P mapping. Okay, so that means that what I want to say is that if you take X, which belongs to P, and encrypt it using this piece of information which is called K, and then decrypt it back using the decryption algorithm and decrypt it using the decryption key, then you should actually get back the original plain text. Okay, that is, you should kind of recover the original message. So that means that essentially the encryption function should be injective, right? That means that that it denotes, I mean, suppose that y is equal to ekx is the encryption transformation, and imagine that if there are two different x1s and x2s, okay, which are kind of distinct, they are not equal, and if you encrypt them using the key k, and you obtain y in both the cases. Okay, so this is an example of a function which is not injective. Okay, then Bob will be confused, right? When Bob receives y and he knows that, okay, he has to decrypt it using the corresponding key, then Bob will not be able to kind of get, I mean, be convinced that whether the plain text is x1 or x2. So that should not happen. Bob should kind of uniquely identify that whether x1 is the plain text or x2 is the plain text. So therefore these kind of functions are not not used. Okay, so therefore we need functions which are kind of which are injective. Okay, so therefore if the plain text set and the cipher text set are the same, then essentially, I mean, for example, if you take alphabets in the plain text set and also the cipher text set is alphabets, then the encryption function is just a permutation. Okay, so if you, for example, the plain text set could be a 0-1 string and the cipher text set is also a 0-1 string, then the cipher text set is nothing but a rearrangement of the 0-1 strings. Okay, so therefore this is an example where I mean you need kind of, I mean, if your plain text set and your cipher text set are the same, then essentially it's a permutation, and the permutation is defined by the key. Okay, because the encryption function and the decryption function are known to everybody, but what is not known is the key. So the key is the kind of material which the cipher designer has to protect, and which the cryptanalyst who is trying to attack will try to recover using some way, I mean, using algebraic techniques, using statistical techniques, and various other methods. So in classical cryptography, we will essentially see two important classes of ciphers. One of them is called the monoalphabetic ciphers, and these are actually some of the primitive ciphers that we have come across. Okay, which means that once a key is chosen, then each alphabetic character of a plain text, so in this case let's consider the plain text to be made of alphabetic characters. So I will be considering the English alphabet, which essentially has 26 letters. Okay, so if there are alphabetic characters of a plain text is mapped onto a unique alphabetic character of a cipher text. Okay, so therefore if I take A and if it maps to C, then it will map to C. So that means that it will always map to C. So it's a kind of unique and fixed transformation. Okay, some of the examples of such ciphers are the Caesar cipher, or something which is more generalized as shift cipher. Then you have the substitution cipher and the affine cipher. Okay, so let us see, I mean, some of them, like but the other types of them are called polyalphabetic ciphers, where each alphabetic character of a plain text can be mapped onto m alphabetic characters of a cipher text. Okay, so therefore each alphabetic character of a plain text can be mapped onto m alphabetic characters of a cipher text. Okay, usually m is related to the encryption key. So which means that if A in case of a monoalphabetic cipher, A will suppose get mapped to C, so that's fixed, okay. But in case of a polyalphabetic cipher, A can be mapped to say m possibilities. It could be mapped to C, it could be mapped to maybe E, it could be mapped to EF, F, and so there can be m possibilities, okay. And usually this m is related to the size of the encryption key, okay. And examples of such kind of ciphers are the Vigenere Cipher, the Hill Cipher, and the permutation cipher. So we also see some of them. Like so, let us start with the most kind of one of the most primitive ciphers, which is known as the shift cipher. Okay, so in case of a shift cipher, let us consider Z26. So you know what is Z26 by now. Z26 means the set. So Z26 is essentially the set 0, 1 to 25. Okay. So these numbers, that is these 26 numbers, can be used to encode the letters from A to Z. Okay. So I am considering that the plain text is made of the letters from A to Z. Okay. So now if you take, I mean a key also belongs to this set, that is from 0 to 25, some of these values, then you can define the encryption function like this. That is, you can take x, and when you apply this encryption function, then you simply add x with k, and then you take a modulo operation with 26. So we have seen what is a modulo in the last day's class. So suppose in that case the letter x, assume that the letter x is A, and suppose the letter k is B. Okay. So therefore A will essentially be denoted by 0, and k, which is B, will be k is B, so B will be denoted by 1, C will be denoted by 2, and so on, right. So therefore what we do is, suppose A, I mean if you take the example, if you take for example that A is denoted by 0, and suppose the key is 2, then what you do is simply you add 0 with 2, and then you take a mod 26. Okay, so there is no problem. So therefore since this number is lesser than 26, so the result is 2. Okay, so therefore that means that A will get mapped to C, right. So similarly, if you want to kind of recover A from C, then you just need to subtract this piece of information. Okay, and this piece of information is nothing but the key, and which is known to the kind of the sender, it is known to the receiver as well. Okay, so it's a very simple kind of function. So it says that ekx is equal to x plus k mod 26, and dkx, which is the actually this should be dky, is equal to y minus k mod 26. Okay, so that, and it is very easy to see that if you kind of apply dk over ek, that is, if we apply dk over ekx, then you get back x. Okay, so therefore this function is indeed an injective function. So a very simple example could be like this. So suppose the plain text is this, that is Force code and 7 years ago. So this is some kind of alphabetic character. You take the, this could be anything. Okay, this doesn't matter, this is just an example. You just have got this encoding, you take this plain text, and a very simple substitution could be like, instead of having A getting mapped into A, what you do is that you shift this by 3 steps. Okay, so therefore A will get mapped to B, C, and D. Okay, so therefore I mean A will get mapped to D. Okay, so that means that what I am saying is this, that is, if you take the characters like this A, B, C, D, E, F, and so on, so if you just add A, I mean rather shift it by 3 steps, then actually you come to this place, right. So therefore A will get mapped to D, B will get mapped to E, and so on. Okay, so you can actually form a table this way. So these are all 3 steps. Okay, so you just these are 3 steps. So therefore in this cipher, if you have got x and there is a fixed shift of this x, you just add with 3 and take a modulo 26, and that is your y. Okay, so therefore in this case this key is fixed. Okay, and this cipher essentially was used by Julius Caesar, and therefore commonly referred as the Caesar cipher. Okay, so therefore the corresponding ciphertext for this particular plain text will be this. So you can see that F will be getting mapped into I. Okay, so that is G, H, and I. So that is 3 steps, and similarly you can actually obtain the corresponding mapping of each of these letters. And this particular cipher was known as the Caesar cipher. And note that the use of the small letter, so we actually what we have done is that we have, for the plain text we have used the small letters, and for the capital letters we have used ciphertext. Okay, this has got nothing to do with the ASCII value, but it is just to improve the readability of the corresponding mappings. Okay, So you obviously understand this is not a very kind of secure cipher, but just to kind of for the completeness sake, if you have got this cipher text, then you can also easily decrypt, because what you just need to do is that you just need to go back by 3 steps. So you know that if the corresponding cipher text is D, you need to go back 3 steps and obtain back A. So similarly, you can actually decrypt this information, and you know that the plain for this particular cipher text, it's easy to obtain the corresponding plain text. Okay, so it's quite easy. Now I will just discuss about something which is a little bit more complicated. So what we do here is that instead of shifting by 3 steps, we shift by some value which lies between 0 to 25. Okay, so the key could be, in that case, an example key could be say 7. What we do is that we take the corresponding corresponding mapping is denoted here, where A is mapped to 7 letters down the line. Okay, but this key actually you would like to change, right? You would not like to keep this as fixed. Okay, so therefore that is the objective. So some of the properties that we will see that so we can actually make changes for the encryption function, but actually it should kind of satisfy some important properties. Okay, that is, each of the encryption and decryption function should be easily computable. We have seen that in case of the Caesar cipher, it is quite easily computable, right? Both the encryption and the decryption are easy to compute. And the other thing is that an opponent, on seeing a ciphertext string Y, should be unable to determine the key K that was used, or the plaintext string X. That is, for an attacker which observes the ciphertext string Y, it should not be able to find out what is the value of the key, because if it gets a key, then you can easily understand what is the plaintext, or it should not also get back the plaintext string some other way also. So therefore that it should kind of leak no information about the corresponding plaintext or the key. So cryptanalysis, as we have already defined previously, is the process of attempting to know this key from the given information. Okay, so we will see that we will see some more concrete examples of cryptanalysis in our next class in context to classical ciphers, and also more techniques as we proceed in the class, but this is the main definition. Okay, so for a Caesar cipher, one way of cryptanalysis will be like, if you know that I mean, let us talk not about the Caesar cipher, because there is no key in the Caesar cipher. Let us talk about the case of the not so simple substitution, where essentially the key can take all 26 possible values. Okay, so suppose you have been provided with a ciphertext like this, then what you can do is that, if you know that this particular cipher essentially is nothing but, I mean, each of the letters has been shifted by k steps, where k can vary from 0 to 25. Okay, so what will you do as an attacker? If you are interested in obtaining the plain text, what you will do is that you will try for all the possible 26 keys, and then kind of start decrypting this information until and unless you get something which is a meaningful piece of information. So if you get a meaningful piece of information, then you can be more or less convinced that since this occurs for all of these letters, and this is a fairly I mean moderate sized string, then you can be convinced that the key is indeed correctly retrieved. That is, the key is in this case 9. Okay, so it says that this particular, because this stems from the fact that you are actually trying all possible key searches, that is, which is called the exhaustive or the brute force search, and you actually get back the key for which the corresponding plain text makes sense. Okay, so this is a very common, I mean, way of doing the doing cryptanalysis. Okay. So in this case, what we see is that the main pitfall is that the key size, or the total number of possible searches that an attacker needs to make, is very small. It's only 26. Okay, so we would first of all like to improve this particular fact. That is, we would like to make it a little difficult, okay, for the attacker. So in this case, one example which is tried here is that the key is some permutation of letters. Okay, so therefore it need not be a shift, but instead of a shift, let us consider which is something which is called a substitution cipher. Okay. So this concept of substitution cipher says like this, that is, if you take A and if you map to J, I mean map say A to J, then B you will not map to J, because if you map A to J and B also to J, then immediately the property of injectiveness is lost, right? So that means that if you take J, then you see that J can actually come from both A and B. Okay, so that is not kind of allowable. Okay, so therefore that will lead to kind of in ambiguity in the decryption process. Okay, so it's not an injective function. So therefore what essentially B will get mapped into is, B will get mapped into something else other than A, okay, than what A has got mapped into. So it could be I. Okay, similarly C could get mapped into something which is not J or I. Okay, so this particular mapping or this particular table can define a particular key. Okay, so this table is essentially suppose kept secret. Okay, So this means that the number of such possible mappings that can actually arise is the first letter can be mapped into 26 letters, the second one can be mapped into 25, the third one can be mapped into 24, similarly to this one. So that means that there are 26 factorial possible mappings, okay, and this number is quite huge. It's more than 2 power of 88 possible keys, okay. That means that the total key size rather is quite large. So that which means that if an attacker would try to kind of try all possible keys to actually obtain back the plain text from the ciphertext, then it needs to do a lot of search, okay, which means that that particular attack method is not possible, okay, but still this cipher is weak, okay, and we will see in our next day's class why it's weak, and or rather how to extract the information of the plain text, okay. So therefore in this case, this is an example of something which is called a substitution cipher, and what you will see is that this concept of substitution cipher still prevails in the modern day cipher, okay. I mean, there are a lot of examples of modern day ciphers where still these kind of concepts are used again and again, okay. So therefore it is, although we know that this cipher, I mean, as independently, if I call this as a cipher, this is weak, okay, but these components actually can be used in the today's ciphers to make a cipher which is more strong, okay, which is much more strong actually. So these are very important concepts that we need to pick up, okay. So but we are never saying that a substitution cipher is secure, and this is still can be attacked, and we will see how it can be attacked, okay. So then we have got something which is called an affine cipher. So what the affine cipher does is that again your plain text and ciphertext are both from this 0 to 25, that is that belongs to Z26, I mean RZ26, and assume that your key is instead of one particular say Z26 element, it could be a tuple, like it could be an ordered pair of A comma B, where A is also chosen from Z26 and B is also chosen from Z26, such that A satisfies a particular property, which means that A is actually co-prime to 26, okay. That means the GCD of or the greatest common divisor of A and 26 is actually 1. Why? Because of it comes from the definition, okay. So what we take as a plain text like X, which is chosen from P, the way, I mean, we choose a K, and then the encryption operation is defined as follows. What we do is that we multiply X with A and then add it with B and take a modulo 26, okay. So from our previous day's discussion, we know that what we can also do is that we can take A and multiply it with X, okay, and then if this number is bigger than 26, then we can take a modulo 26, reduce it to less than 26, and then add B, and again if there is an overflow, I mean we get the result is more than 26, then we again take a modulo 26, okay. If it's equal to or more than 26, then we again take a modulo 26. The decryption operation is defined as like this, okay. So you see that for this decryption operation to exist, rather this function to be injective, you need a particular fact, that is you need that A has to have a multiplicative inverse in this modulo 26. So therefore that means that if you need a kind of I mean in the last day's class we saw that if the multiplicative inverse of A modulo 26 has to exist, then it needs to satisfy a particular property, which is that A should be co-prime to 26, okay. That means that the GCD of A and 26 should be equal to 1, okay. Only then the multiplicative inverse of A exists, okay. So that we have seen in the last day's class on number theory. So that means that all A is not allowable, only those A's are possible or rather are allowed which essentially are co-prime to 26, okay. So how many numbers are there in 0 to 25 which are actually co-prime to 26? So that we need to find out, okay, in order to find out the number of keys. So therefore I mean it's a kind of recapitulation of what we have seen in the last day's class, that suppose A is an element from Zm, then the multiplicative inverse of an element is an element, I mean so is an element B which is also in Zm, such that AB is equal to 1, okay. So therefore AB is equal to 1 modulo M, of course. So then it needs to satisfy a property which is that GCD of A comma M is equal to 1, okay. So note that if M is prime number, then P has a, then every element has an inverse, because GCD of that number and P will of course be equal to 1. So therefore ZP is in that case is called a field, okay. So it's called a field because every number has a multiplicative inverse. But in this case when M is say 26, then every number does not have a multiplicative inverse, because every number which belongs to 0 to 25 set are not co-prime to 26, okay. So we can actually enumerate this and we will find that these are the numbers which are co-prime to 26, like you can see that 1 is co-prime, 3 is co-prime, 5 is co-prime, 7 is co-prime, 9 is co-prime, so on 11, 15, 17, 19, 21, 23 and 25. So how many numbers are there? So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Okay, so there are 12 numbers in this particular set. So that means that all these numbers are actually co-prime to m. So you can actually verify that they have multiplicative inverse, because 1 inverse is equal to 1, 3 inverse is equal to 9. So if you see that if you multiply 3 into 9 you get 27, if you take modulo 26 that is 1. 5 inverse is 21, you can verify this. 7 inverse is 15, 11 inverse is 19, 15 inverse is 7, 17 inverse is 23 and 25 inverse is 25. That means that all these numbers essentially have multiplicative inverse. Okay, so thus the inverse of an element belongs to the above set. So therefore it indeed belongs to the above set, and you can reflect on why. Okay, so therefore the question is, that is, how many numbers are how many possible keys are allowed in this affine cipher. So therefore the a can essentially the value of a can essentially take any of these 12 values, and b can be any of the 26 values. So that means the total key size is essentially 12 into 26, which is equal to 312. Okay, and the key size is of course small, right? I mean, verifying for 312 possible keys is not a very big matter. So that means that the question is that can we generalize this affine cipher? Like, I would like to kind of increase this 26 value so that this size is essentially increased. Okay, so therefore I would like to kind of do a generalized analysis if this 26 is replaced by some value, say m. Okay, so in this case, I mean, I will use the previous day's concepts of Euler-Toshan function, and this is the kind of recapitulation which says that suppose a is greater than or equal to 1 and m is greater than or equal to 2 are integers, and if the GCD of a comma m is equal to 1, then we say that a and m are relatively prime. Okay, so there is the definition of Euler-Toshan function which says that if a is greater than or equal to 1 and m is greater than or equal to 2 are integers, then this is a definition that a and m are co-prime. Okay, then GCD of a and comma m is equal to 1, then we say that a and m are relatively prime. Okay, so that means that if a is equal to 1, this is the kind of case that I would like to make a note, that if a is equal to 1, then GCD of 1 comma m is also equal to 1, and we say that 1 is also co-prime to m. Okay, so therefore there may be a kind of ambiguity about this. Let us make it clear. Okay, so a is greater than equal to 1. Okay, so the definition of Euler-Toshan function is as follows, that is the number of integers in Zm where m is greater than 1 that are relatively prime to m and does not exceed m. Okay, so therefore these numbers are essentially lesser than m. So it will be kind of lesser than m means it will be kind of from 0 to m minus 1, because they belong in Zm. Okay, and Zm actually has 0 also. So the numbers will vary from 0 to m minus 1, and the number of values which are actually co-prime to m, we need to find them. Okay, and they are kind of denoted by some letter which is called as phi m, that is a symbol of the Euler-Toshan function, and this is also sometimes referred to as the phi function. Okay, so as we remember that if m is equal to 26, then we have seen that phi of 26 is 12. If p is a prime number, then phi of p is p minus 1, and if you vary like n from 1 to 24, these are some of the values of phi n, and you can actually see that phi n does not have a nice nature. Okay, it's not a monotonically increasing value with or even a monotonically non-decreasing value. Okay, you will see that if you start increasing n, there are places where actually the value of phi n diminishes, like from 12 to 6 there is a reduction. Okay, so we see that the function is very irregular, and therefore we kind of would like to have a way of calculating the phi m. Okay, so there is a result which says that if m and n are relatively prime numbers, then phi of mn is equal to phi of m multiplied by phi of n. Okay, so phi of 77 will be in this result. If I factorize this as 7 into 11, will be equal to phi of 6 multiplied by phi of 11 using this result, and phi of 6 is essentially equal to phi of 7 multiplied by phi of 11, and phi of 7 is 6. Why? Because since 7 is a prime number, then of course from 0 to p minus 1 there are 6 numbers which are actually co-prime to 7. Okay, so because all the numbers are co-prime, so except 0. Okay, 0 is not co-prime by our definition. Okay, so if you take phi of 11 will be essentially equal to 10. Okay, that is minus 1. So 11 minus 1, again 0 is not there. So that means that this is equal to 10. So therefore that is 6 into 10 is 60. Okay, now what about phi of 1896? So you can again factorize and you will find that it is equal to 3 into 8 into 79, and all of them are prime numbers. So you do a prime factorization, and therefore phi of 3 will be equal to 2 phi of 8. Okay, phi of 8 is phi of 2 cube, and this is not a prime number actually, but if you kind of write that in terms of its prime factors, then this is equal to 2 cube, and we can see that this is equal to phi of 8 will be actually equal to 4, and we can actually see this, right, that phi of 8 is 4. And then you have got phi of 79, which is 78. Okay, so why is phi of 8 equal to 4? You can easily verify this, because if you take the numbers from 0, 1, 2, 3, 4, 5, 6 and 7, that these are the numbers which are belonging to Z8. Okay, you immediately cancel out 1. This is co-prime, this is not co-prime, this is co-prime, this is not co-prime, this is co-prime, and this is co-prime. So there are 4 such values, right? So therefore phi of 8 is equal to 4. Okay, so therefore if I use this fact here, then phi of 3 into 8 into 79 will be equal to 2 into 4 into 78, and that is equal to 624. So this result can be extended to more than 2 arguments comprising of pairwise co-prime integers. Okay, so we will try to kind of again reflect upon the proof which we kind of hurried up in the last class. So phi of mn is equal to phi of m multiplied by phi of n. So what we have done here is that we have kind of laid down the numbers from 1 to, so this is actually 1 to mn. Okay, so actually we should have done from 0 to mn minus 1, but if you see, with the background of the number theory discussion which we have done, you know that it's the same as enumerating it from 1 to mn, because mn, if you take a mod mn, is nothing but 0. Okay, so therefore you can actually enumerate the numbers from 1 to mn. So this is nothing but mn. You see that is mn minus n plus n, so that is mn. Okay, so these numbers are actually written in a kind of array kind of fashion. So 1, 2 and so on till n, and again the next row is n plus 1, n plus 2 and so on till n plus k till n plus n, and similarly there are m rows and there are n columns. Okay, so we need to find out phi mn, which means that we need to find out those numbers which are co-prime to mn, and you note that m and n are relatively prime. So that means that these numbers have to be co-prime to both m and both n. Okay, so it has to be co-prime to both m and n. So first of all, let us see the columns. Okay, so you see, let us try to find out the columns, or rather the numbers which are co-prime to n. Okay, so you see how the numbers are noted down. So these numbers are, if you just observe say a particular column, then you will see that the numbers are like k, n plus k, and m minus till so on like this till m minus 1 into n plus k. Okay, and if these numbers have to be co-prime to n, then by our previous day's discussion we know that the remainder, if I just, for example, if you take n and if you divide it by n, so this number is n plus k, right? If you divide it by n, then the remainder is k, and if this number has to be co-prime to n, then it means that k has to be, the remainder has to be co-prime to n. So that means that the same holds for all of them. You see that this is m minus 1 into n plus k, again the remainder is k, and if this number has to be co-prime with n, then k has to be co-prime with n. Okay, the same holds for this one also. So that means that if this entire column, if k is co-prime to n, then all these numbers are co-prime to n. Okay, so therefore if k is, I repeat, if k is co-prime to n, then all these numbers are co-prime to n. Okay, so that means how many, if I kind from these numbers, if I am interested in finding out how many numbers are co-prime to n, then obviously I need to find out those numbers which, from 1 to n, which are all these possible values of k, which are co-prime to n. And we know by our previous definition that there are phi n such values which are co-prime to n. From 1 to n, there are phi n such values which are co-prime to n. Okay, so that means that there are phi n columns in which all the elements are co-prime to n. Okay, so now let us assume that k is co-prime to n, and let us find out how many numbers among these m numbers, there are m numbers out here, which are actually co-prime to m. We know that in this, again these are numbers like from k, n plus k and so on till m minus 1 into n plus k. We know that there are phi m elements which are actually co-prime to m. Okay, we know that there are phi m values which are co-prime to m. Okay, so therefore we know, if I kind of apply both of them, so there are again, so if I repeat, there are phi n columns which are actually, there are phi n columns in which all the elements, so in the column all the numbers are co-prime to n, and if we just take one of those columns where this particular k is actually co-prime to n, then in this column there are phi m elements which are co-prime to m. So therefore, if I need to find out the number of elements which are co-prime to both m and both n, then we just need to find out, we just need to multiply phi n with phi m. Okay, that is phi n will give us the number of columns which are actually co-prime to n, and if I multiply with phi m, I get exactly those numbers which are co-prime to both m and n. Okay, so that's a kind of very interesting proof and very interesting result. Okay, very useful result. So therefore, phi of mn, where m and n are relatively prime, is nothing but the product of phi m and phi n. Okay, right. So now what we do is that I mean, this is just a kind of conclusion of the previous test proof, and so we can actually apply this to find out phi of p to the power of a. Okay, phi of p to the power of a is nothing but p to the power of a minus p to the power of a minus 1. Why? Now, because this is evident for a equal to 1, we have seen this already, that phi of p is p minus 1. So this is evident. For a greater than 1, let us try to find out what is phi of p to the power of a for a greater than 1. Okay, so the numbers could be like 1, 2 and so on till p to the power of a. So there are how many numbers are there from 1 to p to the power of a? There are p to the power of a numbers in total. Okay, from there let us subtract those numbers which are not co-prime to p to the power of a. Okay, and just little bit of observation, you can actually understand that the numbers which are not co-prime to p to the power of a, or rather which are not co-prime to p to the power of a, are actually p squared, p to the power of a minus 1. I mean, so it's just written like that. It's still like this till p to the power of a. Actually, there should be some dots here. Okay, p square and so on till p to the power of a. So p square, and you just keep on kind of adding on to the power. Okay, so therefore p multiplied with the next power and so on. So how many such powers are, how many such elements are there? You see, if you just observe this the way this p to the power of a has been written, it is p to the power of a minus 1 into p. Okay, so therefore the power here has actually varied from, so there are actually how many possible values? There actually, you will find that if you just find out the numbers of such terms which are there, is nothing but p to the power of a minus 1. Okay, so therefore there are p to the power of a minus 1 values or 1 elements which are actually not co-prime to p to the power of a. So therefore you need to subtract from p to the power of a, p to the power of a minus 1, those numbers which are not co-prime to p to the power of a, and therefore you can actually represent this as p to the power of a multiplied by 1 minus 1 by p. Okay, so this is the same way of writing this. So therefore then if you need to kind of find out the phi of n, then you know that if from the fundamental theory of arithmetic, you can actually factorize any n like this, like p1 to the power of a1, p2 to the power of a2 and so on till pk to the power of ak, and therefore phi n is nothing but phi of p1 to the power of a1 multiplied by phi of p2 to the power of a2 and so on, because of the simple fact that p1 to the power of a1 and p2 to the power of a2 are co-prime to each other. You can actually write them in like this, and then you can actually apply that theorem of, I mean the formula of phi of mn is equal to phi of m into phi of n when m and n are co-prime successively, right? You can apply them iteratively over more than 2 values like m and n, and therefore you can actually get this particular equation. And therefore by the previous thing that you know that phi of p1 to the power of a1 is nothing but p1 to the power of a1 into 1 minus 1 by p1, right? So you know that phi of p1 to the power of a1 is nothing but p1 to the power of a1 into 1 minus 1 by p1. Okay, so similarly phi of p2 to the power of a2 is nothing but p2 to the power of a2 into 1 minus 1 by p2. Okay, so similarly till phi of pk to the power of ak is equal to pk to the power of ak into 1 minus 1 by pk. So now if you kind of find out phi of p1, multiply all these things till phi of pk to the power of ak, then what you get is p1 to the power of a1 multiplied by p2 to the power of a2 and so on till pk to the power of ak into, so this will be multiplied by 1 minus 1 by p1, okay, 1 minus 1 by p2 and so on till 1 minus 1 by pk. Okay, so this essentially can be actually substituted by n itself. So you get n into 1 minus 1 by p1 into 1 minus 1 by p2 and so on till 1 minus 1 by pk. Okay, so this is a formula to compute the value of phi n. Okay, so phi n is nothing but this. So phi n is n multiplied by 1 minus 1 by P1, 1 minus 1 by P2, and so on till 1 minus 1 by Pk. So phi of 60 you can verify. Phi of 660, if you write them as 4 into 3 into 5, then you know that this is equal to 60 into 1 minus 1 by 2, because 2 is the prime factor, and then 1 minus 1 by 3 and 1 minus 1 by 5. This actually works out to 16. Therefore, if instead of 26, if you use 60, then the number of affine keys actually increases to 16 multiplied by 60, that is 960. So that's increased. Okay. So similarly, you can actually calculate the number of affine keys for larger values of m also. Okay. But you need the but you need to keep one thing in mind, that is you need the prime factors. Okay, and factorization, actually this problem becomes more and more complex as you start dealing with larger numbers. Okay. So then we will discuss. So we have actually talked about something which is called a monoalphabetic cipher. That is, once a key is chosen, each alphabetic character is mapped into a unique alphabetic character in the cipher text. Examples of them are shift cipher, substitution ciphers. Okay. So now we will discuss about something which is called a polyalphabetic cipher. So in this cipher, a plain text can be mapped into more than one possible characters in cipher text. Okay. So they are harder to cryptanalyze. Examples of them are the Vigenere cipher and the Hill cipher. Okay. So Vigenere cipher is a kind of polyalphabetic cipher, and each key essentially consists of m characters which are called as keywords, and encrypt. So the idea is that you encrypt m characters at a time, and this was designed by Vigenere in the 16th century. So you can see it's a very old cipher also. So the idea is like this, that is, suppose your example is this crypto system is not secure, this is the plain text, and if you take m is equal to 6, which is the size of the key, and let the key be instead of one number be a pair like this, I mean be a tuple, be a kind of set of numbers like 2, 8, 15, 7, 4 until 17. Okay. So what you do is that you convert the plain text into residues modulo 26 and write them in groups of 6 and then add the keyword. Okay. So that's the idea. So just see that if you see that the numbers are, if you take these numbers like this crypto system is not secure, convert the plain text into this set of numbers. Okay, and then you start writing this key as like this 2, 8, 15, 7, 4, 17. Again repeat this 2, 8, 15, 7, 4, 17. Again keep on repeating as the plain text goes on. Okay. So now you start adding them modulo 26. So therefore, if you take 19, you add with 2, 21 modulo 26, it is 26. So you can get 7, you add 8, you get 15. I mean it's modulo 26, it's 15. So similarly, you start doing this transformation. Okay. So you see that there are two occurrences of 19 here in the plain text, but because of this arrangement of the key, in this case 19 is getting modified by the key material 2, but here it is getting modified by the key material 15. Okay, and as a natural consequence, here you get 21, whereas here you get 8. Okay, so which means that the same plain text as we saw in the monoalphabetic cipher, that this would always have got mapped into a unique letter. Okay, but in case of a polyalphabetic cipher, this letter is getting sometimes mapped into a one number, but sometimes getting mapped into a different number. Okay, and as you can see that since there are 6 possible values in this particular key, this number 19 can get mapped into 6 possible cipher text values. Okay, so that is the basic concept of a polyalphabetic cipher. That is, the mapping is not unique, but it can vary depending upon the size of the key. Okay. So this part of the cipher text here is this, and you can note that the character T is mapped to V and I, so therefore it is called polyalphabetic. There are 2 possible mappings in this shown here. Actually there are 6 possible values. So because that depends upon the size of the key. So we would be interested in finding out what is the key space. Okay, so suppose the keyword length is m, and therefore there are 26 to the power of m possible keys, right? Each of them can be 26 values. So there are 26 to the power of m possible key values. Suppose m is equal to 5, then 26 to the power of 5 is this, which is actually large enough to preclude any exhaustive key search. Okay, exhaustive key search is not possible. However, we will see that there can be still a systematic method to break Vigenere cipher, and that we will discuss in the next day's class. But we see that here that one character could be mapped into m different characters when the character is in m different positions. Okay, so there are m possible mappings of a particular character where m is the length of the key, size of the key. So then we will discuss about a cipher which is called a Hill cipher, which is another polyalphabetic cipher, and it was designed around 1929. So you see that here, I mean we are going more into the modern day ciphers slowly. That is, if you see that m be a positive integer and let p and c both are kind of z26 to the power of m, so that is kind of their m possible values. Okay, so first divide the characters, that is which are there in the plain text, into blocks of m characters. Okay, and then you take m linear combinations of the m characters, thus producing the m characters in ciphertext. Okay, so mathematically it means like this. So let us take a small example where m is equal to 2. So what you can do here is like this, that is, so I am considering the m is equal to 2 case. So let us consider a plain text, say x1 and x2. Okay, so you see that x1 belongs to Z26 and x2 also belongs to Z26. Okay, so both of them are Z26 elements, and you take x1 and you take x2. Okay, assume that you have got a keying material which I, for example, write as, so the key here could be like k1, k2, k3 and k4. Okay, you arrange them in a matrix format. Okay, so where k1, k2, k3 and k4, all of them are chosen from Z26. Okay, so then you define your operation as this. The y, which is the ciphertext, is y1, y2 is equal to nothing but the multiplication of k1, k2, k3, k4 multiplied with x1, x2. Okay, so if you need to find out the x1, x2 from this, then obviously you need the inverse of this matrix. Okay, so therefore the inverse of this matrix needs to be defined. Okay, so you can actually see an example here, that is, it says that y1 comma y2 is equal to x1 comma x2, and therefore you can actually write it's written out like this. Okay, so it could be like the matrix is either pre-multiplied or post-multiplied, but so it depends upon the way it has been arranged. Like it is arranged as a 1 cross 2 in this case, so vector, and so therefore the multiplication you have to appropriately apply, pre-multiply or post-multiply, depending upon the way you are writing this x1 comma x2 pair. So this vector. So what is essentially done is that if you break up, right, these are nothing but linear transformations of this order. Okay, so therefore y1 is, instead of 11x1 plus 3x2 mod 26, and y2 is 8x1 plus 7x2 mod 26, which has been written in this way. So this 11, 3, 8 and 7 are actually the piece of information which is the key. So you see that this is a slight extension of the affine cipher, and it goes closer to the cipher concept that we have today, which is called the block ciphers. Okay, so it's a kind of a bridge from these classical notions to these modern notions. Okay, so you see that here you can actually write that as y is equal to xk, and where y is equal to y1 comma y2 and x equal to x1 comma x2. So all these operations are performed modulo k, but the important point is that for the injectivity, as we have seen in context of affine ciphers, we need the inverse of this keying material. Okay, so therefore you see that given a plain text x, we get a ciphertext y, but in order to have the inverse, we actually need the inverse of this matrix. Okay, if you know that if the inverse of a matrix exists, that is, if you take k and there is a k inverse, if you multiply and you get back the identity cipher, then immediately you know that if you take y and if you multiply it with k inverse, then that is nothing but y can be written as xk from the definition, that is y is equal to xk, then y is equal to xk and then multiplied with k inverse. So you know that k and k inverse, if you multiply you get im, and therefore x of im is nothing but x. So therefore you obtain back the plain text x. Okay, so therefore the important criteria is that the inverse of this matrix needs to exist, right? So thus for Hill ciphers to work, the matrix k must be invertible. There should be an inverse which is called k inverse. Okay, now we know that when so this is an example we can work out. So therefore the important condition is that k needs to have an inverse. So we say that k has an inverse if and only if the determinant of k is invertible in Z26. Okay, we know from our basic course in matrix algebra is that k inverse is nothing but 1 by determinant of k, and this is the kind of, you know what this is, so you can write them as a cofactors. Okay, so therefore using the cofactors. Okay, so therefore the most important thing is that you can always multiply, but the thing is that this determinant k and inverse of that needs to exist, which means the determinant k's inverse needs to exist. Okay, and when will the determinant of k inverse exist in modulo 26? It can exist if and only if the GCD of the determinant of k and 26 is equal to 1. Okay, so this is quite easy to follow from our previous description. That means that k is an inverse if and only if the determinant of k is invertible in Z26, and that means that if and only if GCD of determinant of k and 26 is equal to 1. So therefore the formal definition is like this. So you take x, you multiply it with xk, and decryption is also defined as this, but only it needs to be an invertible. Okay, so therefore you can actually compute the size of the key using this. A slight extension of this is called a permutation cipher. All previous ciphers include substitutions where you actually have taken a plain text character and replaced it by a different ciphertext characters, which also forms a very important component of modern ciphers, substitution ciphers. And then the other component is a permutation cipher, which will keep the plain text characters unchanged, but will alter their position by rearranging them using a permutation. Okay. So suppose x is a finite set, a permutation over x is a bijective function, and you know that which is denoted by pi, which is from x to x, it's a mapping, and thus the inverse permutation is actually again back from x to x and defined by pi inverse. Okay, and it is defined by the rule as follows, that is pi of inverse of x is equal to x dash if and only if pi of x dash is equal to x. Okay, so therefore that is the definition of a permutation cipher. Okay. So what you can do is that you can take from x1 to xm, so these are suppose the numbers like which forms the plain text from x1 to xm, and then you start rearranging them. Okay, so x1 goes to a different location, x2 goes to a different location, and so on, but the basic characters, the set of characters remain unaltered. So therefore x, the index of this is denoted by pi 1. So what essentially gets kind of transformed is the index locations, right? You take, so any permutation you can actually denote like this, like you take x1, x2 and so on. What you are doing is a rearrangement, right? In a permutation you are just doing a rearrangement, so these locations get changed. Okay, so x1, so this essentially becomes x1, which essentially was x2 in this case. Okay, so we will actually denote them as x of pi 1, x of pi 2 and so on. Okay, so if there are m values, then x of pi m, so all of them are nothing indicating that the characters index positions are changed. Okay, so therefore you can actually denote them using this, that is this is the notation of the permutation, and this is an example here, like you take 1 2 3 until 6 till 6, and therefore what you have done here is that you have just kind of transformed them from, so 1 goes here to 3, 2 goes to 5, 3 goes to 1, 4 goes to 6 and so on, and similarly you can define the inverse permutation also. Okay, so this so therefore you can actually, there is a small comment made here, the permutation cipher is a special case of the Hill cipher. Okay, so I leave it to a kind of exercise to reflect upon this point, that is why is it so, and just give you some points to ponder. That is, one of them is that you have to comment on whether the Euler-Tauschen function for n greater than 1 is even or odd. You need to kind of give an argument in your favor, and express permutation cipher as a Hill cipher. So these are some problems given to you. So among the references that I have used is Farhad's Cryptography and Network Security, and next day we will be discussing about the cryptanalysis of classical ciphers.